The reaction types lab will determine what type of reaction a whole bunch of different experiments are. Remember, there's 5 basic reaction types: combustion, synthesis, decomposition, displacement, and double displacement. Now we're seeing a whole bunch in demos, so those are included here as well. And then these are the experiments that we are doing inside. There's a bunch of reactions, and we're telling you what the products are. We're not balancing them for you. So you've got to obey the law and balance the equations. And then following the pattern, you want to know what type of reaction to call this. This is really the words we use, the language of chemistry. And we're dealing with some hazardous chemicals here. So we got to wear gloves, we got to wear goggles, we got to protect ourselves from lab hazards. We're going to be using thermometers to determine if they're endothermic or exothermic. We're going to be using some indicators, like universal indicator, that shows whether something is an acid or a base. Remember, red is acid, purple is base, purple or blue. And there's a really particular chemical that we're going to watch out for in this lab, silver nitrate. Silver nitrate can turn your skin into a weird color. I can show you. I'll take off my glove and put a new glove on. I got an exposure from a demo that I did. I wore my gloves, but then when I was cleaning up, I got some on me. So see that weird color? You probably don't want that. So the reaction types lab is basically to understand the language of chemistry and to learn how to balance equations. We're going to see a whole bunch of different reactions, a whole bunch of different chemicals. And in the lab report, it's going to ask you about those polyatomic ions. So just remember, there's a whole bunch of polyatomic ions. Here's many of the ones that we are likely to see. And don't forget to include the ones from the demos. Okay, all the demos that we are going to include in this lab are the Carbohydrate Demo with Dextrose, the lighting the Bunsen burner demo, the match and the Bunsen burner. The match is a reaction, the Bunsen burner is a reaction. The magnesium, brighter than the sun reaction, that's included. And the thermite reaction. So they're all listed here on your lab, and you want to figure out which category those are in. So you might try to like circle them and connect. It might be hard to do that. So what you might want to do is next to them write, you know, combustion, synthesis, whatever they are, next to them on here. You do have to identify what reaction type those are as well, and we will be balancing them on another page of the lab. And then pay attention to these reactions, pay attention to what happens, and try to understand where those products are. Are they solids? Are they gases? Are they coming out in what form? Also, look for the signs of a chemical reaction. One sign is a change of indicator color. That's a sign. Change of temperature on your thermometer. That's a sign of a chemical reaction. A precipitate forming. Okay, light, evolving a gas, you know, making bubbles is evolving a gas. So we're going to have really big reactions here. Normally we do this in a well plate. So this placard was actually designed for a well plate. Notice, this is designed for this particular well plate. Fits right on top of it. So because we're doing it instead in beakers, we are going to get big reactions, much bigger than we would normally get in our lab room. So this is one for the video. This is one that you can see on camera. Notice that all of these liquids look pretty much the same. That one looks like water. 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 That one looks like water, but they're not. This one, as I said, can turn your skin different colors. This one, very hazardous, hydrochloric acid. You probably know that on the street. Well, this one actually is water. This is distilled water, so that one's fairly safe. Of course, we never would taste lab chemicals. This one is lead nitrate. That contains lead. That's a hazardous chemical. That's one reason we have to wear gloves. And this one is potassium iodide. They're going to be combined. This beaker is actually empty. They're going to be combined in that central beaker. So I got to get a new glove on. I'm actually not going to perform this lab myself. I'm going to have my lovely assistants perform the reaction types lab. Okay, so now we've got a couple more demos. Actually, it's a total of 4. We're going to start off with the hydrogen peroxide demo. The hydrogen peroxide demo is an example of reaction types. Remember, we talked about these reaction types. Which one is it? So think about that. Hydrogen peroxide is a funny chemical. H2O2, kind of a funny looking chemical. Kind of looks like it should be this one, right? It should be regular old water. Well, what does it have to lose to become like water? It has to lose one of those oxygen. So if it loses an oxygen, well, then the oxygen flies away. Well, oxygen has to be like this, actually, O2, right? Oxygen has to be like this. And what we are left behind with is water. So how are we going to get this started? Well, actually, it's already started in here. This reaction is already going. So I'm going to lower in the thermometer, and we're going to see what the temperature of this reaction is. Right in there. Down deep, but not touching the bottom. It's got to be in there, but not touching the bottom. And the temperature of this reaction is 23 degrees Celsius. Okay? So let's just watch this reaction. Let's just watch it. But that's kind of boring. It's a very slow reaction. So what we're going to do to speed it up, oh, I've got something here. I've got something we can use. I've got a little catalyst. Catalyst is a chemical which speeds up reactions. Well, this catalyst is called manganese dioxide, MnO2. Don't get that confused. That's not magnesium. That's manganese, and it looks like a powder. Let me take a scoop out. It looks like a little gray powder, okay? So what I'm going to do is I'm going to add some, and we're going to see this reaction accelerate, because this is a catalyst. So watch, I'm putting a little more in, a little bit in. Now notice, we see a reaction. It's happening way faster now because of the catalyst. Also, you see some sort of fog developing there. So that looks like that should be oxygen, right? Should be oxygen, right? But actually, oxygen is completely invisible. Think about it. You're breathing oxygen right now. You can't see the oxygen in front of you. So oxygen is invisible. What you're actually seeing there, what you almost always see when you think you're seeing a lot of gases, it's actually water. It's actually water turning back into liquid in the air. So I'm going to add more now. That's not enough. I'm going to put more of the scoop in, and we're going to see this reaction speed up. So now notice, this is the reaction. We're producing oxygen and water. So maybe some of that is water vapor, but actually you can't see water vapor either. You're seeing it when it turns back into liquid. So what's the temperature on here? Well, now it's getting up to 30. It's rising.
It's like going up, bouncing.
Is that a pretty good reaction?
It's like bouncing.
It's like bouncing. And it's splattering a bit. This always happens with this reaction. So the great thing about that reaction is that provides us with one of the things we need for our next reaction, which is actually the oxygen. That's one of the things we need. So I'm going to let that reaction keep going. That will, if anything, that's going to accelerate our next demo. Okay? So notice I'm not in harm's way being right here, because what's being given off is actually oxygen and water. That's what that is. So I'm not being harmed here, but there's extra oxygen in this area. Maybe we can take advantage of that in our next demo. The next demo is the magnesium demo. Okay, magnesium is an alkaline earth metal. Magnesium is an alkaline earth metal, and it usually comes in ribbons like this. Okay, we find that the good stuff, for some reason, comes from India now. This is a ribbon of magnesium. Remember, metals are malleable. Metals are ductile. So you can make them into wires, and you can make them into sheets. Well, guess what? A ribbon is a little bit of both. It's almost as thin as a wire, and it's as flat as a sheet. So here's a little piece of magnesium metal. The problem is it's in the presence of oxygen, which is what it needs to react, but it's not reacting. To start this reaction off, we are going to have another reaction that's easier to start. So let me find another reaction that's really easy to start. I'll move this out of the way. Oh, you know what's easy to start? A safety match. That's why matches were created, because they're really easy to start. Okay? So lighting a match is actually a chemical reaction. So to see this one, I'm going to turn the light off right there. So I'm going to light the match, and then I'm going to use the match to light my stovetop. Okay? That's going to ignite the methane, mostly methane, that comes out of the stovetop. That reaction will get going, and then I'm going to use that reaction to start my magnesium ribbon, which will take advantage of this extra oxygen that has been introduced from my previous demo, if it's still in the air, if it's still in this area. Okay? So this is actually 3 reactions. One of them is lighting the safety match. The second one is burning the stovetop. Normally we would use Bunsen burners, but this is a same gas, the natural gas, mostly methane. By the way, methane doesn't smell. They put a little additive that really stinks so we can detect gas leaks, by the way. That's not the methane that you're smelling. So first of all, let me turn this on a little, and then I'm going to light the match. That's one reaction. Second reaction. Okay, I put the match out. Now I'm going to use that to light the magnesium ribbon. Now this is a very bright reaction, so just make sure to avert, those of you that are in the room, my kids, just don't stare at it for too long. Try to avert your vision. Okay, you want to see it, but you want to also not blind yourself. Okay, so this one is a little harder to get started on a stovetop than it is with a Bunsen burner. There we go. So now I got 2. It's like a binary star. Is that as bright as the sun? Look at all these shadows. See the shadows forming? Look at all these shadows forming. That's what they use in flares. This is a really good one. This is a really, really good one. Okay, I'm going to have to turn on the expeller fan. Okay, this is a really, really good one. It's burning brightly, maybe because of that extra oxygen. Maybe because of that extra oxygen that is here. This one's going for a long time, a really long time, right? Okay, that is a great reaction, a great example of an alkaline earth metal demo. Let me shut off the stovetop. And notice how bright that was. That was, if depending on your distance, I'm a little dazzled right now myself. That was as bright as the sun, and I did 2 ribbons, so it was kind of like a binary star. Well, there's the magnesium oxide. Lots of chemicals oxidize, and then they form compounds with oxygen. Lots of chemicals react with oxygen. Magnesium is no exception. So remember that you need to determine what reaction type that was. Of those reaction types, which type of reaction was lighting the match, which type of reaction was the actual stove burning, the gas burning, the methane, and the magnesium, the alkaline earth metal. Okay. The other one, of course, was the hydrogen peroxide that we did first, and that reaction is now pretty much over. So look over here. What's left? Oh, no, it's still going. And our temperature, oh yeah, look, 85 degrees. It reached 85 degrees Celsius, so it took a while to get there. I think that might be the maximum temperature. Shut this off. I think that might be the maximum temperature for the hydrogen peroxide, about 85 degrees. Yeah, because now it's going down to 84. So I think, and it's actually still bubbling just a little bit in there, getting close. See, it's really just bubbling a little bit in there. And what's left in there is actually the catalyst is still in there, because catalysts are not directly involved in the reaction. Catalysts are still in there, and water. So if we used up all the hydrogen peroxide, then what we really have left in here when this is done is water and the catalyst floating around. It should settle on the bottom. So in a few minutes I'll get another shot of it after it has settled out on the bottom. Okay, thank you guys. Thanks for doing the demo with me.
Yeah.
Now you can see a few minutes later that it is just water. You can see right through it, and the catalyst has settled on the bottom. The catalyst was there, but was sort of a bystander. That's why it is left out of this reaction. So you don't consider the catalyst when you're figuring out the reaction type or balancing. demo involves carbohydrates. Carbohydrates, like these guys, are made of, just like they sound, carbon and hydrate. Well, when you need to get hydrated, don't you drink water?
Yeah.
So they're carbohydrates. They contain carbon and water mixed together. So carbohydrates. So I'm going to be pouring sulfuric acid into a little crater that I'm making in the carbohydrates. I'm pouring it into the dextrose, about 20 milliliters. I'm pouring it into the sucrose, same amount. And a smaller amount, I'm gonna see how much sugar is in French toast by trying to write a little letter on it. Oh, I messed up that a little bit. Oh well. So now let's see how this works out. Sulfuric acid versus carbohydrates. Sulfuric acid is acting as the catalyst. We're going to remove the water. And what are we going to be left with, Mr. Guerra?
Carbon.
Just the carbon. So if you didn't believe there was carbon, let's move closer now. If you didn't believe there was carbon inside that very white sugar, well, here it comes. Powdered sugar, dextrose, C6H12O6. Let's see the carbon come out of this. Let's see the carbon that's in here. The great thing about powdered sugar is it starts much faster. Oh, there we go. There we go. There we go. That's a monster. Epic, epic monster. A monster for the ages, Mr. Guerra. So, we've got the thermite reaction, the big reaction, the thermite. We're reacting aluminum versus iron. Who's gonna win? Who do you think's gonna win? Aluminum is gonna win. So that's in here. But before that, we're going to try the initiating reaction with this black powder. This is the way we used to start the reaction with potassium permanganate, but this reaction isn't reliable because these chemicals have been kind of shoddy. Then after that, we're going to start off the thermite reaction. We're by a busy street, so it's a little noisy. We're going to start off the thermite reaction in here using the flash demo. The flash demo is going to start it off. Flash demo is magnesium with silver nitrate. So that's going to be something I'm going to add in here on top of this. So right now inside this one we have potassium permanganate. After the initiating reaction, we're going to react these two chemicals. We're going to react basically what amounts to rust. It's the same thing as these little pieces of rust I found off of a little bench. It's hematite. Hematite is rust, and then this one is aluminum powder, which is the same thing that is in aluminum foil, which I have right back here. It's the same exact thing as aluminum foil, just in powdered form. And then I've mixed them together, and notice that the color you don't even see the aluminum anymore. All you really see is the hematite because it overpowers the aluminum, it coats it. We're going to do a few neat tricks in here. One of them is we're going to try to melt an ionic compound. Remember, ionic compounds or salts are very hard to melt. Here's one, this little cube here. It's very hard to melt because of the ionic compound structure, like this. You can shake them a lot, they're really not going anywhere. So you can shake them and shake them. It takes about 800 degrees Celsius to melt these, which is like 1,500 Fahrenheit to melt them. So it's hard to use a thermometer. We don't usually, oh, and I've got a little piece of this right here. This is the same as a small one. I think it'll be easier to melt a small one. Another thing we're gonna do is have an actual thermometer. We don't usually do this. This thermometer is probably gonna be destroyed by this reaction, but I have it set on max. So it'll record the maximum temperature. It'll record the maximum temperature that it reaches, okay? Also, I'm going to use a little bit of cellulose or paper, because cellulose famously, remember this? Cellulose famously will begin to combust if you reach that temperature. You gotta put some sand on it to hold it down, okay? And I'll put the salt on top. If you reach that temperature of Fahrenheit 451, okay? Of course, Fahrenheit is garbage. Fahrenheit we don't really like to use in science. It's a terrible, terrible scale. So what do we use? Celsius. In Celsius, that's 233. 233 Celsius. But there's an even better scale, better than Celsius. What is it? Do you know? Kelvin. So what we're really going to reach, well, 506 Kelvin is when that paper will spontaneously burst into flames. So if you see that paper burst into flames with no match, we've reached that. This will record a temperature. This will probably go bye-bye. We won't worry about that. And the ionic compound will melt. There's one more thing I want to try. One more thing I want to try. Because, remember, one ring to rule them all, one ring to bind them, one ring to bring them all, and in the dark, I think I misquoted that. Anyway, Lord of the Rings. So in honor of Lord of the Rings, I'm going to put a little piece of platinum in here. This will probably be okay. We'll see if it melts the platinum. I'm going to put that in there. I'm going to put it next to the ionic compound. So we'll have a little bit of platinum, a ring, like if this is Mount Doom, because this is going to come out as hot as lava, maybe it'll melt the ring or just start to melt the ring. We'll see what happens to this piece of platinum and this ionic compound. A metal and an ionic compound. They're going to be smothered with a whole bunch of the products of the thermite. The products of the thermite are going to be alumina and iron, molten iron. They will come out at a temperature that is hotter than any lava, anywhere, any lava. So this is the main reaction, but before that, we're going to try a little side reaction, the initiating reaction. That's the first one, the initiating reaction. So my lovely assistant Lucy, come closer, is going to put glycerin, which is this one, into the potassium permanganate. Go ahead, Lucy. Put it in, put a big dollop. And this should start, that's enough, stop. Yeah, that's good. Now walk away back behind the safety line, thank you. This should start off a pretty flashy reaction. Quiet. There it goes. There's the initiating reaction. So now notice it's smoldering, but it really didn't do all that much. That's kind of what I expected. I'm going to try to start it with a squirt bottle. I'm going to try to spray just a drop of water in there is all it takes to start it. There we go. Whoa! Woo! Perfect. Now I am making a little crater into the thermite materials, and I'm adding the materials for the flash demo. This is quite a bit. This is the magnesium, and the silver nitrate, as you see over there. Now when they're dry, they have no problem with each other. It's only when they get a little bit wet that they react. So I'm putting the flash demo right on top. All it's going to take is a drop to get this one going, and then when this one goes, Ian, wait, come over here, Ian, so you're back there, and show the squirt bottle. Stand back there. Don't squirt. Stand over there so you're in the camera. Ian's going to squirt with the squirt bottle, not from here, not from here. Not right now. Okay, you're going to squirt it. Now go back. And his little drop of water that's going to land in here is going to start off the flash demo. It's going to be flashy, really quick. Then the thermite's going to get going. Like lava, hotter than any lava on Earth or Mars or Venus or anywhere. It's going to pour out onto the one ring to rule them all, and onto the ionic compound, and onto the cellulose, Fahrenheit 451. So what we're going to see is, these are 3 ways of measuring how hot it gets. Does it get hot enough to melt ionic compound? Sodium chloride, that's 801 degree. Thermometer might survive, we'll see. It'll tell us how hot it was over here. The paper, if it bursts into flames, that's Fahrenheit 451. I'm going to try to grab it while it's molten and show it to you and to my kids. And it's a little hot, so I've got my thermal gloves. All right. So Ian, you can move up to squirt it. You can move up to here and then step back. He's squirting right now. Squirt that, not the camera. Squirt. Watch it. Watch it. Stand back. Here it goes. That's going to get it going. That's going to get it going. That's going to get the thermite going. Look at this. Look at this. That's a good thermite. Whole lot of thermite. Whole lot. Molten material flowing out. Okay, let me see. Okay, I think the thermometer is actually still survived. Did the paper burst into flames, guys? Did the paper burst into flames?
Yeah.
Good.
That was so cool.
Look at how big this chunk is. Oh, wow, molten. Molten, right? Oh, it's burning up my papers. Uh-oh. So we might, okay, I was gonna see if it was magnetic. Oh, it's still molten. Here's a magnet. Nope. Okay, look at that chunk. Let's try to tap some out. Let's try to tap some out. Look at that. Look at that. Look at that. Molten. Is that cool? Hotter than any lava. Hotter than any lava. We didn't. You can see the products. You can see the ring. What happened to the ring? You can see the ionic compound. Very melted right there. Look at that. And then this is all shiny, sparkly. Let's see. Magnetic. So let's see, that's the initiating reaction on the top. Watch. Watch the bottom, watch the bottom, watch the bottom. Come on. There it goes, molten iron. Molten alumina. Molten iron and alumina. Look at this, look at this. Molten, oh, look at that. That's why we have a circle. Look at that. Let's see. Hopefully this will happen. We want to see a really strong one. We want to see a really strong reaction starting. Come on. More than that, way more. Way more than this. There we go, that's what we want. That's what we want. There we go. Watch the bottom. It's gonna come out. It's gonna come out molten. There we go. This is why we have a safety perimeter. Wow. Okay, now, Mr. Pemble is going to do this. Again, watch your feet. Mr. Pemble is going to try to pick up all that thermite. And watch this. Oh, this has got to be on camera. Can I get some to spill out? Oh, it's already solidified. Usually I can get some to pour out on the bottom. Woo! Still going, let's try to light it. Oh, yeah. Whoa! Next time use tongs. Mr. Pemble, Mr. Guerra. There we go. came out the bottom. We've got a huge amount here of product here. Okay, glowing like lava. Pour some out maybe. Ground. Wow, it's spectacular. Look at this glowing product from the demo. Okay. So the reaction types lab is going to be performed by my beautiful assistants. And they are gonna take turns doing the experiments and measuring the temperatures. Say hi, guys.
Hi.
Okay, so let's get started. Could you move the paper over? And let's get the first experiment. The first experiment involves, look, this one. Zinc and hydrochloric acid. So where's the zinc? Where's the zinc? There's the zinc. And where's the hydrochloric acid? There. Now it looks kind of like water, doesn't it? Looks all kind of harmless. Let's measure, go ahead and measure its temperature. We're going to get the temperature before, what would you say that is?
23.5 Celsius.
Good. That'll be our before temperature. Now, Lissy, go ahead and add, what are you adding?
The universal indicator.
What does that show you, Lissy? Universal indicator.
It shows me if it's an acid or a base.
Do you know why they call it an indicator?
Because it indicates which one it is.
Do you know what the original indicator is? The original indicator is this finger. This is your indicator finger. It points at whether you've got an acid or a base. So what do you think this is going to turn? Predict. What's it going to turn? What color?
I don't know.
Is it called hydrochloric acid?
Acid.
So what do you think it's going to turn?
Red.
Let's see. Put in some squirts. We're doing it on a big scale, so we're putting in more than the instructions call for. Okay, there we go.
That's red.
So that's pretty reddish right now. Liquid colors are different than colors on paper, but I'd say that definitely falls in this range over here, right? Wouldn't you say? Would you say?
Yeah.
Okay, so we are going to be reacting that with the zinc. So go ahead and pour it in, and I want to get a good shot of the reaction. And once it gets going, Giovanna's going to get the temperature,
Doing this one?
yeah, into the zinc. Just pour most of it in. We're doing a big scale reaction. Okay, that's good. That's enough. That's good. That's a good reaction. So I knew this might foam over. I had a suspicion. Now that's a good reaction.
Oh, wow.
There we go. There we go. Get the temperature, Giovanna. The only drawback is this could damage our white background, but if we need to, we'll get white placards.
42.9 Celsius.
Can you give me any information that students might want to know right now?
Oh, it's really,
It's turning darker. And it's bubbly a lot.
And what else?
it's like,
What about a smell? Come
oh
on.
yeah, it smells really bad.
Yeah, please. So the students can't smell it on videotape. So see all this? This is the dog of chemistry. Lucy, what is the dog of chemistry?
Wait.
What is the dog? The one that barks. The one that barks is hydrogen, the most abundant element in the universe. Look at that cool bubbling effect.
I'd say like 76 point.
Oh, has it gone up that much?
Yeah, it keeps going up.
Wow, wow, hang on. So this is a good one. It's really going. We know whether the temperature went up or down. That's the main thing. And you know what I think I'll do? I think I'll just swap out the placard with a laminated placard. The reason I didn't is because I wanted to, because of the reflection, but oh well. We've got laminated placards. Yeah.
Okay.
Okay, now let's switch the paper. I think we're on the next page now.
Yeah.
And we might have to move the other paper over here, yes, so that it's more visible, because these are the reactions we're doing now. These are the next reactions. We're going to be reacting two chemicals with this dread silver nitrate. Copper with silver nitrate and magnesium with silver nitrate. There's the copper, there's the magnesium, and we need to get the temperature of that before it starts. So let's get a temperature.
23.2 Celsius.
Yeah, that's probably the temperature in this room. What is it right now?
23.3.
Okay, we'll say that's the temperature before. Giovanna's going to pour it into the copper. And she's just going to go ahead and pour the rest into the magnesium. So let me turn these so that that's not blocking it. Let's see what kind of reaction we're getting here. So do we see any signs of a chemical reaction? Any signs of change?
Not yet. This one's fizzing very slightly though.
Don't you notice any sort of color changes?
Oh.
This one's the copper and this one is the magnesium.
Yeah, on the copper it's getting darker.
Darker, right?
Yeah, but the above it is just normal.
Well, let's see if there's a change of temperature. Lucy, see if there's a change of temperature in the copper one.
Okay. It's 24.0.
So a very small, if any, change of temperature. Now wipe it off and then put it in the other one.
This one is 26.0 Celsius.
Okay, so there is a change of temperature. So for some slow chemical reactions, you might not get a real dramatic bubbling or anything. But, I mean, I do see signs of chemical reaction. What's the biggest sign that something is happening here?
Probably bubbling or changing color.
Changing color. Yeah, because look at that. That doesn't look like copper anymore. And that doesn't look like
Oh, it just started floating to the top.
magnesium anywhere. Yeah, so then that means there must be some bubbles there to lift those things up to the top. The bubbles stick to them sometimes and elevate them. So what do you think all that gray stuff could possibly be? All of that goopy, gross gray stuff. What do you think it must be?
The silver nitrate.
It came out of the silver nitrate.
Yeah.
So look at these reactions. What gets kicked out of the silver nitrate? What gets kicked out of the silver nitrate? What has that gray color? What do you think? Any guesses?
No.
What if I were to tell you that all of this gross gray stuff coating the other metals and sometimes on the bottom is silver?
Really?
Yes, that is silver. So silver is being kicked out of the silver nitrate. That gives you a pretty good idea what kind of reaction it is, by the way. And there it is. There is the silver.
Okay. This one's 24.0.
Okay, still a small change.
This one is 28.7, 29.0 Celsius.
29, okay. So they both had small changes of temperature. One of them was more than the other, but they were similar kinds of reactions. Both of them were metal reacting with, some metal reacting with silver nitrate, producing this. I don't want to give away the reaction type, okay? And this one was a metal reacting with silver nitrate. So again, that's the chemical that can change your skin color. So I think what we're going to do now is we're going to switch gloves just to be safe. You guys switch your gloves before the next experiment. Okay? Okay, so now we're going to move, let's move the paper over here. Now our next experiment is this one. Okay, we are going to be reacting these two liquids with each other. Let me come around for a second to say which reaction it is. Okay, we are going to be doing the potassium iodide and the lead nitrate. So lead, any chemical with lead is a little hazardous. That is this one. So we're being very careful with these chemicals. So we're reacting potassium iodide and lead nitrate. Now look, these are both colorless liquids. Well, that one might be a little bit off color, but it was clear when I first put it in. These are two seemingly clear liquids, and we're going to combine them here. So Giovanna, get the temperature beforehand. What is the temperature?
23.1 Celsius.
Okay. And then she's going to take the temperature of beaker C, which has the lead nitrate. Let's go. Good job wiping it. And what is it?
It is 24.0 Celsius.
Okay. So they're pretty similar. What was the first one again? Well, let's just say they're both around 23, 24 degrees. Okay, that's probably all we need to know. So now Lucy is going to pour beaker A into B. That's an empty beaker. Just pour it in. And now she's going to add beaker C. So she put the potassium iodide in there. Notice it's clear. And now she's pouring in the lead nitrate.
Whoa.
Do you see any signs of a chemical reaction?
Yes.
Get a temperature.
It happened right away.
Some reactions don't mess around. Some reactions are instantaneous, right?
Oh yeah, but it stayed
It'd be
around 20. So 24.4 Celsius.
Okay, just give it a second. It has to adjust. But 24.4. Okay, and then we'll measure the temperature again in a few minutes. But
It's
okay.
the yellow.
Is that pretty?
Yeah.
Okay. So the lead iodide has a pretty color. Now, does it look like it's a liquid right now? Would you say that's a liquid?
Yeah.
Yeah.
Okay, so let's come back and look at it toward the end of the lab when we're all done, or even a few minutes after we're done. We'll let it sit there and I'm going to come back and look at it.
Okay.
Because if it's really a liquid, if it's really like a solution, then it should stay like that for like a long time until like the water evaporates or whatever. So let's just see how long it stays like that. Okay, we'll come back and check it out later. Let's get one more temperature of that right now, because we can assume the reaction has peaked. It seems like it happened very quickly.
24.4 Celsius.
So 24.4. So if it went up like 0.4, right?
Yeah.
Very little. Okay, so that will help you determine if it's an exothermic or endothermic reaction. Just remember, some reactions are just barely in either category. Some of them just barely register. Okay, that's a pretty one, right? So our next reaction is going to be the calcium oxide. Don't have a cal. Calcium oxide plus water. So calcium oxide is this white powder. See that white powder? And it is known as quicklime. That's one of the ways that we find calcium. If it's been lying around, it oxidizes. But after this reaction happens, what we wind up is called slacked lime. Okay, these are chemicals that we sometimes use in cement. Sometimes going from this to this is one of the reasons that cement works. Did you know that? Like sidewalks that you walk on? Okay, take the temperature of the water right now, Lucy. Get the temperature before, and then we'll talk about the
It's
reaction.
at 23.7 Celsius.
Good, 23.7 Celsius. So Giovanna's going to add the universal indicator to the water. What color would you expect it to turn?
Green.
Okay, that's what we'd expect. Let's see what we get. Put a good squirt in there. Oh yeah, that's a nice green.
Yeah.
Okay, so now we've got that, and now we're going to add, that's the water, we're going to add the calcium oxide to it and see what happens. Just go ahead and put it in there. Most of it. Now for this one, you might have to stir it up a bit. So get your stir rod. Do you see any colors?
Purple. It's getting lighter. It's like a violet.
Okay, so what does purple indicate?
It indicates.
What does purple indicate?
Purple indicates that it's a base.
Right, now do you know why it's a base? Because bases generate hydroxide. Bases generate hydroxide, and look, can't this generate a bunch of hydroxide? Okay, let's get the temperature after. The reaction is pretty much full blown at this point.
It's at
Give it a second to adjust. Any changes?
24.0 Celsius.
So very little change of temperature. They're very slight change of temperature. But even with a little change, you can tell if a reaction is endothermic or exothermic. So using a thermometer before and after, you can tell which category it falls in. Some of them might only change very slightly. Now, do you notice anything else now? Anything else happening here?
You can see.
Bottom is kind of white.
You can see the powder
So the powder is settling where?
on the bottom.
On the bottom. So now let's go back and look at that yellow one before we're done. By the way, that was our last reaction for this set of reactions. Let me just mention a couple of others. Unless anything there?
It looks like orange juice.
Look at it from the side.
Yum.
Oh, you can see like, you can kind of see some stuff on like the sides.
Yeah, so we're going to come back and look at it in a few more minutes, and we're going to see what's happening here. Also, I think that reaction's still going. That's funny. Okay, so by the way, there's a few reactions here that we did not just do. This one is part of that demo. This is lighting a match. This is the strip on a match. This is the safety match head. This is the reaction for the match. This is what happens on a stovetop or a Bunsen burner. So these are the ones, I had these up because these are other reactions we want to classify. So I'll be doing those demos. Those are all part of this lab with the match and the stovetop, which would normally be a Bunsen burner. Then we'll use that to light the magnesium. So remember, all of those reactions are considered part of this lab. So thank you guys for helping me with these experiments. You want to say bye-bye?
Bye.
Good job. One thing we did not get around to was measuring conductivity. So I'm going to check the conductivity of all of these things right now. And we're going to start off with the first experiment, the products of the first experiment. Let's see if that's conductive. Can I get it in there? Okay. And then I want to wipe it off. Wipe it off on here. Then I want to see the products of the second experiment. And get them to, oh, there we go. Okay, wipe that off as much as I can. And then the third experiment. Okay, wipe it off. And then the fourth experiment, I should be able to reach more easily here. Don't want to go too deep in there. Okay. And let's see our last experiment. Is this one right here? Let's see, does that conduct? Does that conduct? Okay. Clearly it does. So we've got good conductors, that's electrolytes. And what about, well, we still have this acid here. Let's check for this acid. Is acid a good conductor? What do you think? Is acid a good conductor? Acid is actually the best conductor, the best electrolyte because of that moving proton. And let's take another look at these beakers now. I see a lot of stuff down there. Can you see that? Maybe I should pick it up and hold it upwards. Notice if I shine the light through it, the light shines through some of that, but on the bottom we see what is called a precipitate. Okay, so that's one thing. What about this one? Well, same situation. Look, there's clearly powder on the bottom. Okay, and then the rest of it, of course, is that dark purple color. Very good contrast here. It's almost like, just like this. An acid on this side and a base on that side. It's just like the universal indicator colors go there. So I think we've seen enough to be able to determine everything about these reactions. And then along with the demos, you can identify which reaction types that we saw. So now that we've waited about a half hour, let's take a look. Okay, that looks about the same. What about, oh, wait a second, look. Look at that. It's really, really settled out. So remember, some things appear to be liquid, but they're not. If the solid eventually settles at the bottom, that was not a solution. And that is what we call a precipitate. Precipitate actually means to throw down. Like when it's raining, the clouds are throwing down water on you. And this one is also interesting looking. Look at all that silver. We could be rich if it wasn't so gross. Look at all that silver again. Okay, so these reactions have completed now. And this reaction also, I believe, I don't see any unreacted material. So that kind of sums it up for the indoor reactions for the reaction types lab. let's see. Put in some squirts. We're doing it on a big scale, so we're putting in more than the instructions call for. Okay, there we go.
That's red.
So that's pretty reddish. Right now, liquid colors are different than colors on paper. But I'd say that definitely falls in this range over here, right? Wouldn't you say? Wouldn't you say?
Yeah.
Okay, so we are going to be reacting that with the zinc. So go ahead and pour it in, and I want to get a good shot of the reaction. And once it gets going, Giovanna's going to get the temperature, into the zinc. Just pour most of it in, doing a big scale reaction. Okay, that's good. That's enough. That's good. That's a good reaction. So I knew this might foam over. I had a suspicion. But that's a good reaction.
Oh, wow.
There we go. There we go. Get the temperature, Giovanna. The only drawback is this could damage our white background, but if we need to, we'll get white placards.
42.9 Celsius.
Is it-
I know, it just keeps going up. I'd say like 76.
Oh, has it gone up that much?
Yeah, it keeps going up.
Wow, wow, hang on. So this is a good one. It's really going. I think this is in focus. Looks good. Let's see if we can get a little closer. Vigorous reaction. Look at them flying around in there. Lucy, can you see that from the side on your side? They're just flying around.
Ugh, smells horrible.
Good, that's what I wanted to mention. It's nasty. Hydrogen smells nasty with a Y. Okay, so... So let's get a temperature. Yeah, that's probably the temperature in this room. What is it right now?
23.3.
Okay, we'll say that's the temperature before. Okay, now Giovanna, I'm going to get a good shot here. Giovanna's going to pour into the copper. And she's just going to go ahead and pour the rest into the magnesium. So let me turn these so that that's not blocking. Let's see what kind of reaction we get here. So do we see any signs of a chemical reaction? Any signs of change?
Not yet. This one's fizzing very slightly though.
Don't you notice any sort of color changes?
Oh.
This one's the copper and this one is the magnesium.
Yeah, on the copper it's getting darker.
Darker, right?
Yeah, but the above it is just normal.
Well, let's see if there's a change of temperature. Lucy, see if there's a change of temperature in the copper one. So a very small, if any, change in temperature. Now wipe it off and then put it in the other one. Okay, so there is a change in temperature. So for some slow chemical reactions, you might not get a real dramatic bubbling or anything. But, I mean, I do see signs of chemical reaction. What's the biggest sign that something is happening here?
Probably bubbling or changing color.
Change in color. Yeah, because look at that. That doesn't look like copper anymore.
Yeah,
That doesn't look like
oh, it just started floating to the top.
magnesium anymore. Yeah, so then that means there must be some bubbles there to lift those things up to the top. The bubbles stick to them sometimes and elevate them. So what do you think all that gray stuff could possibly be? All of that goopy, gross gray stuff. What do you think it must be?
The silver nitrate.
Came out of the silver nitrate.
Yeah.
So look at these reactions. What gets kicked out of the silver nitrate? What gets kicked out of the silver nitrate? What has that gray color? What do you think? Any guesses?
No.
What if I were to tell you that all of this gross gray stuff coating the other metals and sometimes on the bottom is silver?
Really?
What?
Yes, that is silver. So silver is being kicked out of the silver nitrate. That gives you a pretty good idea what kind of reaction it is, by the way. And there it is. What is the temperature?
23.1 Celsius.
Okay. And then she's going to take the temperature of beaker C, which has the lead nitrate. Let's go. Good job wiping it. And what is it?
It is 24.0 Celsius.
Okay, so they're pretty similar. So now Lucy is going to pour beaker A into B. That's an empty beaker. Just pour it in. And now she's going to add beaker C. So she put the potassium iodide in there. Notice it's clear. Now she's pouring in the lead nitrate. Do you see any signs of a chemical reaction?
Yes.
Get a temperature.
Happened right away.
Some reactions don't mess around. Some reactions are instantaneous, right?
Oh yeah, but it stays
It'd be
around 24.4 Celsius.
Okay, just give it a second. It has to adjust. But 24.4.
Okay,
Okay, and then we'll measure the temperature again in a few minutes. But
It's
okay.
yellow.
Is that pretty?
Yeah.
This should not change its temperature. Okay, that's a nice color. Now, is that what you expected?
Kinda, yeah.
What does green indicate? Green indicates
Neutral?
neutral. Like water is neither really an acid or a base. Well, actually, it's both. But anyway, from one or the other at a time. Okay, so now what you're going to do is you're going to dump the powder into there. The calcium oxide is going in. So you might wonder, why are we using an indicator? That's probably enough. And then you might have to stir it up. Do you guys notice anything?
Oh, it was a dark purple and now it's getting lighter and lighter.
It's a violet.
But it wasn't purple at all to begin with, right? It was green, wasn't it? So what does purple indicate? Oh, we get this right here. Let's turn it. What does purple indicate?
It's a base.
Purple indicates that it's a base. Now remember, this is called an indicator because the original indicator is your index finger, so it's indicating that it's a base. Okay, aluminum bromide demo. Little piece of aluminum into the bromine. Contact. The bromine is a liquid. Bromine is one of the only liquids on the periodic table. Okay, other than mercury. We're getting a reaction now. Look at that. It's reacting, producing a product. Aluminum bromide. The challenge for this lab is to figure out the molar mass of this aluminum bromide. Reaction. This aluminum bromide orange gas that is billowing away uses up an intense reaction. It's great. Let's close this up a bit. Try to use up all the bromine because we don't want to put it back in the storeroom. And this is the end of this beaker. This is doom and destruction. This particular beaker will not be using the Farky beaker again. I'm glad I got a video of that. That was one of the best ones. It's going to completion. It's using up all of the aluminum. Okay. It's a heavy composition of that stuff.